Okay, our next speaker is Professor Zapata, and he will be telling us about loop quantization as a continuum limit in quantum gravity.
Okay, first, thanks to the organizers and thanks to you that you are here to look at this talk. Where is the pointer? Okay. This is a conceptual talk and it's short, so I'm going to go slowly, but don't be scared because there is not much explicit material given. I just want you to understand very few things, and that's it. So the point of view that I'm giving here is slightly different than some other points of view of other people that do loop quantum gravity. And here I'm taking loop quantum gravity as I applied a process that I call loop quantization to gravity. And if you want to be more precise, I use some particular variables. Okay, but it's a process that could be applied to other frameworks. In particular, to other gauge theories like Young-Mills or something, I can loop quantize them and try to see what I get. Also to sigma models. So they have to be gauge theories, but they can be. Okay, and the takeaway idea for the whole talk is that the loop quantization can be considered a continuum limit of lattice gauge theory, but it has to be complemented with something else. So to all the structure that we have in loop quantization or loop quantum gravity, we have to add a regularization map. And then I will show in that context that, yes, we can get together with this regularization map a precise statement of being a continuum limit of in the many aspects that it needs to be there. And that's what the talk is about. Okay, so I start with the results and with the main idea of what is this regularization map. So here is what I already said, but in a formula. This is the space of generalized connections, if you want. And I'm saying that this space can be obtained somehow in terms of a sequence of some other spaces that I'm going to define here. And the equality here means that I have a space that I generate with this thing, and then I take a completion, and then I get this one. So in more mathematical terms, the space that I will get is dense here, and then when I complete it, I get the whole space here. So let me just explain what is this space, and I don't know if everyone here is an expert on loop quantization, but loop quantum something, but at least the main ingredients you will have heard. So this A here is a parallel transport map. It's a connection, and I use it to take, say, path order exponential or somehow to obtain an element of a group. Okay, so the ones that I'm going to consider, the ones that are elements of this A tilde, that's what I'm defining, and is a subset of all the possible connections here, are the ones that preserve some equivalence class that I define here. So see that this is a space-time, if you want, or if you want space, this is a manifold where I'm going to be doing parallel transport. And parallel transport just assigns group elements to curves, and I have these two curves that are actually not the same. No, they are different. But with respect to this triangulation that I have here, that is, I see it as the composition of the manifold in cells, and I have here cells of dimension 2, dimension 1, and dimension 0. To each of them, I can associate a sequence of cells. So first, they start in this two-dimensional cell, then they pass to this one-dimensional cell, then to this two-dimensional cell, then anyway, these two have the same, they follow the same journey in the sense of cells. They are different, but for the cells they are the same. So I could have another curve that is very similar to this red one, but then exits in this direction, and then that would be different. Okay, so I have this equivalence, this red one and this blue one are equivalent in this sense of the triangulation. And then if the connection is such that it assigns the same parallel transport to all the paths that are equivalent, I call these connections this cellular decomposition, let me call it delta, so they will be delta flat. Okay, in the sense that when something is flat is when the parallel transport doesn't depend on the path. If I have one starting point and one end point, something senses curvature when the parallel transport depends on the path. Okay, so this will be flat in this particular way with respect to the coarseness that the cellular decomposition lets me see. So it's like a resolution scale, what I just set up. And then if I refine this triangulation, I can see, I allow more curvature, and then I can see more details. And so these spaces, these delta n's, they will be, if I have a delta 1 that is coarser triangulation and delta 2 is inside delta 1, then there is a natural, they are contained in each other. Okay, so the delta 1, if it's the coarser triangulation, it will have very few possible connections. And delta 2 that is finer, it will include more connections because all the ones in delta 1 that are flat at this scale of delta 1 are also flat in the scales of delta 2. And so I get a way in which I allow more and more connections, flat connections. Okay, so this is the space that I wanted you to understand, and that contention is what I call a regularization map. So one important thing is that the space of these connections, you can associate it with the space of connections in a lattice. So here I have this yellow triangulation. If I draw something that is called the barycentric subdivision, I just add more lines, and I get a lattice. The space of lattice connections will parameterize the space of these delta flat connections. Okay, and this is usually like the group to the number of edge lengths. No? So okay, let me see. So this is the result, about the space of fields, that I obtained the whole space of fields in the loop quantization as a limit. And then what happens to physical measures? If I get the measures, or better said, states in the sense of this algebraic talking of the previous talk, okay, in this sense of algebraic quantum field theory, if I get states that let me calculate expectation values and correlation functions, then I can import them from the triangulation at the scale n to the continuum by this regularization map that I gave. You just include the things, and also with this inclusion map, you push forward the measure, and then this gives you a measure here that lets you take expectation values of things here, or functions there. Okay, and then why is this interesting? Well, here, I can play the game of renormalization a la Wilson. And with that, if I have more than one of these things, I can go to critical points and do everything that the people do in the lattice. And after I have this collection of possible lattices with measures, I embed them all here, and I want to ask whether they converge to something physical or not. After I did all the running of the coupling constants, and I found the fixed point and all that, then I will get a way to calculate expectation values here that converges. Okay? So if it converges, I call it the continuum limit measure, even though maybe it's not a measure, it's just a thing that lets me calculate expectation values and correlation functions. Okay, so this was all in general. Let me go to examples. In the continuum, everyone knows that the 2D easing model is a great model because it's actually analytically solvable. So it's a non-trivial model that people already understood mathematically at very precisely. Okay, so using these mathematical results of here, then we can see that the continuum limit of the 2D easing model does produce for us a quantum field theory that converges. And it's not only convergent, but it satisfies the Weidmann axioms and everything. So it induces a relativistic quantum field theory, and you can say that it's loop quantized. Okay? So it's a very non-trivial example. And this other example, you know, when people started doing loop quantum gravity and realized that it's a very difficult thing, they went to do the easiest example possible that captures some of the mathematical properties of loop quantization, and this thing was called polymer quantum mechanics. Okay, when you have polymer quantum mechanics, you have a representation of the Heisenberg algebra that is not equivalent to the usual one. And then you get some very crazy things happening. But if you do want to take the point of view that I'm taking and you need to take a continuum limit, then the craziness goes away and you get, at the end, after you renormalize, in a sense, that is a very, very mild renormalization because it is quantum field theory in one dimension only, then you get standard Schrödinger quantum mechanics. And this is a very general thing. It holds for any potential that is convex. Okay, so what are the lessons after I gave the general results and then the two examples? Lessons, scale. Here, scale, I introduce it as coming from a triangulation or a set of triangulations that I said I was going to refine. But you can take it for any cellular decomposition of a manifold. And it sounds a little strange because this is completely not covariant or said in a very crude way regarding a triangulation. But you can say it also in a fancier way, saying that this thing induces a set of algebras, and these algebras are related to each other with this regularization map, and also with the other map that I didn't talk about because it's a usual one that we have in loop quantization, that is a coarse graining map. So here we have some sets of algebras that have a partially ordered and directed structure in joining them, and joining them also there are regularization maps and coarse graining maps. And with this, you get what I told you before. Another lesson is about physical observables. So imagine that you run this setting and you get finally a theory and you want to add something to the theory, something that you really want to measure. And then these observables need to be such that the limit that I write converges. And the limit that I write was exactly, I didn't even write it, but I said that it was the same thing as I would do in the lattice. So I will have to do something statistical, some like Monte Carlo simulation or something, and get in the space of fields and do some sampling. And these things would not converge if they are very punctual things. They have to be somehow extensive. They are the only things that converge. So like measuring angles between things is something that one knows from intuition that is not going to converge. If somehow you measure things that are going to be local, but using collective behavior or some extended things, maybe they will converge. Okay, but things that from the beginning are just local, they don't. Physical observables, and then 1 minute. Yeah. So phases in loop quantum gravity. We already saw in the dynamical triangulation talk that there are phases in dynamical triangulations. Can we see them in loop quantum gravity? And for that, what is useful is to have some order parameter. No? And in gauge theories, Wilson told us almost everything, including what are the good order parameters. And they are the Wilson loops. And there you have to see how the Wilson loop changes when you change the C, but there is with respect to the background structure. And here you don't have background structure. What you have, if at all, is the metric that the state gives you, so the quantum gravity scale. So you will have to see how this changes with respect to the quantum geometry. And just a warning is that you need time-like curves and time-like surfaces to say things that are interesting. And so challenges, what do we need for all these things to work? We need something very important. It's called a renormalization prescription. And when you have a Hamiltonian that is gapped, for example, you need the first energy difference, or maybe you want to have a correlation length or something. So in gravity, we need one. And it would be nice to have something that is, in a sense, local, because we have everything kind of diffeomorphic invariant. And then it would be natural to see if we have a piece of space-time, then maybe in this region of space-time, you do have a Hamiltonian, just a boundary term, and study if that can give you a good renormalization prescription. But this is just I'm giving this proposal, but the main message is that we need something that gives us a renormalization prescription to run the renormalization group in reverse. And in this view of loop quantization, I'm sacrificing diffeomorphism invariance, but I'm thinking that in the continuum limit, it may arise and come back, as it happened in the 2D Ising model, and that's it. Okay. Thank you.
I'm afraid we don't have enough time for questions, so
sorry.